Welcome to Chemistry 101, Chapter 4, Selected Problems. A 24.7 gram sample of limestone calcium carbonate contains 9.88 grams of calcium. What is the percent calcium in limestone? So what is the percent of calcium in calcium carbonate? And you have a 24.7 gram sample, and 9.88 grams belong to calcium. And it wants percent. So this is calcium, this is limestone, and you multiply that by 100%. Whenever you're doing these, it's the part over the whole. And the part is always smaller than the whole. Think of a pie. So a part of a pie, this part is smaller than the whole. And so when you're doing percentages, you do the part that you want over the whole. You're going to definitely need to be using your calculator for all of these, so you might want to get that out in your periodic table. 9.88 divided by 24.7 times 100, because it's percent, there's your units, that is 40.00% belongs to calcium. How many sulfur atoms are in 0.2 mole of sulfur dioxide? Okay, so we can go from mole to numbers of atoms or molecules or units. So whenever we have how many, usually you want to think, oh, we need to do Avogadro's number. And you don't have to memorize Avogadro's number. If you look at your periodic table that you're given, and you'll have this for your exams, you see Avogadro's number is 6.0221 times 10 to the 23rd. In this case, it would be atoms equals 1 mole. It's always going to be equals 1 mole. So that's a conversion factor, and so you have 0.2 mole of sulfur dioxide. You're going to have to do a lot of dimensional analysis. So remember we did this in chapter 1 where we copy the letters down that we don't want. So here is what I call the given. That's what's given. You always find it with a number and a unit. So you're always going to start with that. Basically put that over 1. That's where you start. That's your given. And then you say, okay, what's the question asking for? How many sulfur atoms? So we know Avogadro's, for 1 mole of sulfur dioxide, we can have 6.0221 times 10 to the 23rd atoms. Now we get our calculator in and we multiply the top. So 0.2, you can take divided by 1, but that won't, make a difference, times 6.022 second EE to the 23rd. It gives me 1.204 times 10 to the 26 atoms. And then your significant figures will always be however many numbers are there. So obviously you can just do that. But technically that's even 2 significant figures and that's 1, but we're not going to worry about it. Okay, calculate the molar mass of each of the following. The molar mass, you have to look at the periodic table. And you're going to use that average atomic mass provided. And you'll add those up. So here we have, you see we have 2 mercury and we have 2 chlorine. And so this is 2 times, and you look for mercury, Hg, and you see that the average atomic mass is 200.59, and that's grams per mole. You want your units. Usually you can take it out 2 past the decimal, and that'll be fine. So sometimes you'll have 3 and 4 past the decimal, but 2's good. I sometimes do that and sometimes don't, but I at least try to take it out past 2. Chlorine is 2 times 35.4527. 2 times 200.59, 401.18. 2 times 35.4527 is 70.9054. And then we add that up, plus 401.18, and that's 472.085 grams per mole. If you want to take it out further, like I did here, you can, but I would say at least 2. Okay, that's A. What about B? We have calcium, you have sulfur, you have 4 oxygens. Here we have, this is a hydrate, 2 times 2 is 4 hydrogens, 2 times 1 is 2 oxygens. And so calcium, when you get the periodic table, you see is 40.078, sulfur is 32.066, oxygen is 4 times 15.99994, so 16.00. 4 times 1.008, oxygen, oh, we have more oxygen, so 2 times 16. All right, and then we're going to sum all these up. I'm going to put these together, so I'm going to say 6 times 16 takes care of my oxygen, plus parentheses 4 times 1.008, that takes care of hydrogen, plus 32.066, plus 40.078. That gives me 172.176 grams per mole. And that's for B. This one's A. Okay, here we have C. We have 2 chlorine plus 5 oxygen. So 2 times chlorine is 35.4527, and oxygen is 5 times 16. And we're going to add these up. 2 times 35.4527 plus 5 times 16, 150.905 grams per mole, and that is C. And for D, we have 1 sodium, 1 hydrogen, 1 sulfur, and 4 oxygen. Sodium is 22.989768, that is 23 if you round to 2. 1.008 for hydrogen. Sulfur is 32.066. Oxygen 4 times 16. And we add all those up. 4 times 16 plus 32.066 plus 1.008 plus 23. 120.074 grams per mole for D, sodium bisulfate. The hydrogen makes it bi. Calculate the number of moles in 10 grams of the following substances. Okay, so our given is 10 grams. And for whatever the substance is, so for like A, that would be potassium bicarbonate. The number of moles is the question, so we got to go from grams to moles. And how you do that, you need a conversion factor, and that's a molecular formula. So you're going to do dimensional analysis here for 1 mole of KHCO3. But we need to know what the grams are, and that's your formula weight, your formula mass. So let's add potassium, hydrogen, carbon, and 3 oxygens, just like we did previously, to get our conversion factor. 39.0983, 1.008, 12.011, 3 times 16. And so that is 3 times 16 plus 12.011 plus 1.008 plus 39.0983. That's 100.117 grams per mole. And what that grams per mole means is that's 100.117 grams of KHCO3 equals 1 mole of KHCO3. And that's the conversion factor. So we can then put this number in right here, 100.117. And now you see that you take 10 grams divided by 100.117, you get 0.09988 mole, because these cancel out and you're left with mole of KHCO3. And then you say, okay, I need 3 significant figures, so 0.0999 mole is the answer for A. Okay, B, well, what's the formula weight? 2 hydrogens and 1 sulfur. So 1.008 times 2 plus sulfur is 32066. So 2 times 1.008 plus 32.066. So the formula weight for B, 34.08 grams of H2S equals 1 mole of H2S. That's our conversion factor. So we take 10.0 grams H2S, and we have 34.08 grams H2S and 1 mole of H2S. So now you do 10 divided by 34.08, and you should get 0.293 mole of H2S. Now I have lots of numbers on my calculator, but because the given has 3 significant figures, I've rounded that to 3. All right, C, selenium. Well, selenium is just an element, and it's 78.96 grams per mole. So for C, you can just say 10 grams of selenium, and there are 78.96 grams of selenium in 1 mole of selenium. 10 divided by 78.9, 0.12, and now this is 67 mole, and the 7 is going to round the 6 up, so 0.127 mole of selenium is the correct answer. Okay, now we're doing magnesium sulfate. So magnesium is 24.3050. Sulfur is 32.066. And 4 oxygens are 4 times 16. So if we sum this up, 4 times 16 plus 32.066 plus 24.3050. Then for D, our conversion factor is 120.37 grams of magnesium sulfate equals 1 mole of magnesium sulfate. And then you can do the 10 grams of MgSO4, and for 120.37 grams for 1 mole of magnesium sulfate. So we'll take 10 divided by 120.37, and we get 0.0831 mole. Calculate the mass. Mass is grams. So of 250 mole, 2.50 mole of substances. So now we're going from mole to gram, and we still need to do the formula mass. So for A, we have barium hydroxide. We have 2 oxygens, 2 hydrogens, so we have to add that up. Barium is 137.327, 2 times 16, 2 times 1.008. 171.34 grams per mole. And so now you can do 2.50 mole of barium hydroxide. And then you copy those letters down, mole of barium hydroxide for gram of barium hydroxide, because the mass is grams, that's what you want. This is your given, so you start here, 2.50 mole over 1. And now you put in your numbers. For 1 mole of barium hydroxide, you have 171.34 grams. That's your conversion factor. And now you know that you have to take 2.50, multiply it to 171.34 to get your answer. And that gives you 428.35 grams. You'll see that the moles cancel out and you're left with grams. And that's your answer for A. B, 2Cl equals 2 times 35.4527. So 2 times 35.4527. That's 70.905 grams per mole. And we're starting with 2.50 mole of chlorine. That's one of your diatomics, one of the 7. And for 1 mole of chlorine, you put that on bottom because you don't want that. You use the molar mass, 70.905 grams of chlorine. And now you know that cancels out, and you know to multiply 2.50 times 70.905. And they give you 177.26 grams of chlorine. And if you did want 3 significant figures, it would be 177 grams of chlorine. Okay, for C, we have 2 potassiums, 1 sulfur, and 4 oxygens. So 2 times 39.0983 plus sulfur, 32.066, plus 4 times 16 for oxygen. That gives you a formula mass of 174.26 grams per mole. And so we come down here and do C. We're doing 2.50 mole of potassium sulfate. And for 1 mole of potassium sulfate, we have 174.26 grams of potassium sulfate. And that is 435.65 grams. And now we'll do D. This is phosphorus trifluoride. So for phosphorus, we have 30.9737 plus fluoride 3 times 18.998. And that formula molecular mass would be 87.9677 grams per mole. And then we start with our given, 2.50 mole of PF3, phosphorus trifluoride. And for 1 mole of PF3, we have 87.9677 grams of PF3. And you can see that the moles cancel out. And then you can take 2.50, multiply that by 87.9677, and that gives you 219.919 gram. And once again, that would round up to 220 grams of PF3. A sample of ammonia weighs, that's what's in Mr. Clean, ammonia, weighs 30 grams. Calculate the following quantities. So this is our given. This is what we're going to start with. 30.0 grams of ammonia. We start with that over 1. And then we're going to write grams of ammonia on bottom. Sorry, excuse me. Because that's what we don't want. But now we have to read the question to figure out where we're going to. So here we want moles. So can we go from grams to moles? Yes, we use that the formula way. So what's the formula mass of ammonia? Nitrogen and 3 hydrogens. Nitrogen is 14.01, and hydrogen is 3 times 1.008. And so we have 3 times 1.008 plus 14.01. We have 15018 grams per mole. And so we can do 15.018 grams for 1 mole of ammonia. And you see that the grams of ammonia cancel out and you're left with moles. That's what you want. So all we had to do now is to do 30 divided by 15.018. And our answer for A is 1.9976 mole of ammonia in H3. We need 3 significant figures, so this will be 2.00, because the 7 will round that up, mole of ammonia. All right, so let's do B. B, the number of molecules. You need to do Avogadro's number, because the number of molecules is 1 mole equals 6.0221 times 10 to the 23rd, and it can be anything. In this case, it's molecules. So you have to go, so we're at grams. You're starting with 30.0 gram of ammonia, and you got to go from gram to mole to number of molecules. And when you go over these little, this is the formula weight, this is Avogadro. These are your conversion factors that you're going to use to get there. So here, gram of ammonia, you calculate that down for mole of ammonia. But that's not what you want. It wants number of molecules. So for mole of ammonia, you have molecules. Now notice I didn't put any numbers in, because right now I just want to make sure that my units are going to cancel out from grams, moles, to give me what I want. And it does. Now I can put the numbers in. So here, 15.018 goes with grams, 1 goes there. And in this conversion factor, 1 goes with mole, and 6.022 times 10 to the 23rd goes with the molecules. So now I know to take 30.0 divide by 15.018 times 6.022 second E to the 23rd to give me 1.203 times 10 to the 24th. Don't forget that, because you know if you had to take this and move this decimal 24 places, this is a big number. So you must have your times 10 to the exponent for it to be correct. Okay, C. C is very similar number of nitrogen atoms, except it wants nitrogen atoms. So we're going to need another conversion factor in there. We're going to have to say for 1 mole of ammonia, we have 1 mole of nitrogen. Because if it, you'll see that it'll make a difference in the hydrogen here. So here you're going to go from the grams, you got 30.0 gram to mole to, so mole of ammonia to mole of nitrogen to Avogadro's number of atoms. So here we do 30.0 gram of NH3. We're going to do gram of NH3 for mole of NH3. Mole of NH3. See, that's a substance, but we want mole of nitrogen, so then we got to go to mole of nitrogen. And then mole of nitrogen for Avogadro's number of atoms of nitrogen. And then we can put in our numbers, because you see that grams cancel, moles cancel, mole of nitrogen cancels, and then we're left with atoms, and that's what we want, atoms of nitrogen. All right, so you know this is 15.018 goes with grams and 1 goes with mole. You have to get these right, these numbers, because otherwise you're multiplying when you should be dividing and vice versa. For 1 mole of nitrogen, we just came up with this conversion factor from the formula. There is 1 mole of nitrogen. And for 1 mole of nitrogen, we have 6.022 times 10 to the 23rd atoms. So now that we have our numbers in there, we're ready to get our calculator and go 30.0 divided by 15.018 times 1 divided by 1, so I just don't do that, times 6.022 second E to the 23rd. Now I have 1.203 times 10 to the 24 nitrogen atoms. And you can even round that up to 1.20 times 10 to the 24th nitrogen atoms. That's the answer for C. Now let's do D. Okay, so D, we have 30.0 grams of ammonia, NH3, grams of ammonia. So we're going to go from grams of ammonia to, we got to get to mole of ammonia. You know that's going to be your formula weight. What was that, 15? Let me see, 3 times 1.008 plus 14.01. That was 50. Oh, I've been using the wrong number. 3 times 1.008 times 14.01 plus 3 times 1.08. I was thinking that was wrong. Okay, so go back and change that, and your number will be slightly different, okay? I'm not going to actually go work it, but I'm just letting you know right now the correction was 17.03, so you can go back and work that. If it's slightly different, no big deal in your answer. Okay, but anyway, that is the actual correct formula mass. Okay, so you need the formula weight to get from grams to moles, and then where are we going? We want moles of hydrogen atom. So to mole of hydrogen, you can change that mole to mole. So for 1 mole of ammonia, you have 3 moles of hydrogen. Because you see this, there's 3. So then we are going to say for a mole of ammonia, we have mole of hydrogen. So we have our letters in there, and our letters cancel out. Gram ammonia, gram of ammonia, mole of ammonia, mole of ammonia. We're left with mole of, oh, it wants hydrogen atoms. Okay, mole of hydrogen atoms. So because it asks for atoms, they want Avogadro's number. So mole of hydrogen equals hydrogen atoms. And you can cancel that out because that's the same thing here. All right, so now you want to put in your numbers. So right here, 1703 grams per 1 mole. For 1 mole of ammonia, we have 3 moles of hydrogen. And for 1 mole of hydrogen, we have 6.022 times 10 to the 23rd atoms. 30 divided by 17.03 times 3 times 6.022 to the 23rd. And 3.18 times 10 to the 24th hydrogen atoms is correct. Which of the following molecules have an empirical formula that is different from their molecular formula? All right, so your empirical formula is in the lowest terms. So like when you eat sugar, like table sugar, that is C6H12O6. And that is produced by photosynthesis, so you might have seen that. So that would be a molecular formula. It's like the true formula. The empirical formula would be if you reduce these to the lowest terms. So 6 can go in 6 one time, 6 can go into 12 two times, and 6 can go into oxygen 6 one time. So this is the empirical formula. So it's the lowest terms. And most of your inorganic solids are the empirical formula, but your molecular solids, your molecular compounds, are the molecular formula. So here, hydrogen peroxide. Well, you would not want to drink a liter of hydrogen peroxide. Okay, so that's very different than water. But hydrogen peroxide, that is the molecular formula. Because what's the empirical formula? It would be HO, lowest terms. So that one would be different. This one here, this is formic acid. That's okay, you don't know that right now. Formic acid is what causes that stinging when you have ants that bite you, the biting ants. But you see that's really H2CO2. Because carbon's 1, that is your lowest terms. So here the empirical formula equals the molecular formula. So this is the same. This is different. N2O4, well, that's a molecular formula. Because what's the empirical formula? NO2. So that one would be different. SiO2, which is sand or glass, that is in its lowest terms. So the empirical formula equals the molecular formula here. What is the empirical formula for each of the following? So we're going to have to take this down to lowest terms. 2 will go into 4 2 times, 2 will go into 10 5 times. So you find the lowest common denominator, and then you reduce that down, and that would be the empirical formula. Here, this is the empirical formula, because 2 and 5 do not have anything, a low common denominator. This one, lead 4 chloride is its lowest terms. And here, let's kind of gather it all together. We have 2 hydrogens plus 8. We're going to have to kind of gather these. C4, how many carbons do we have? C4, 5, 6. We have how many H's? 8, 9, 10. How many oxygens? 4. So you can see that this can be lowest common denominator can be 2 because of the 10. So C3H5O2 would be its empirical formula. What are the empirical formulas of the compounds with the following compositions? Okay, so when you are asked for empirical formulas and you're given percents, then you need to do these steps. I'm going to give you step 1 through 3. Step 1, you want to change percent to grams. That's the easiest thing because you're just changing the unit. Step 2, you want to go from grams to mole. And you do that how we've done that with the periodic table and the formula mass. In this case, you'll use the elemental mass for the elements. And then step 3, you're going to divide by the lowest number of moles to get the subscript. The subscript is the lower number. So the whole point is you want the formula, so you want the subscript. So here we have iron. So this is what you're looking for. You're looking for X and Y, the subscripts. Well, for step 1, we do 72.36. Instead of percent, we say gram of iron. Okay, step 2, we're going to convert gram of iron to mole of iron. And I do this by looking at the periodic table, and I look for iron, and I see 55.847 grams for 1 mole. And so I do 72.36 divided by 55.847, and that's 1.2957 mole of iron. And then I'm going to go back to the same thing for oxygen, 27.64 grams of oxygen, and grams of oxygen for 1 mole of oxygen. I look at the periodic table and I see that's 16.00. And so now I take 27.64 divided by 16, and I get 1.7275 mole of oxygen. So at this point, I'm on step 3, okay? I have to divide by the lowest number. Well, what's lower, 1.29 or 1.72? So 1.29. I'm going to divide both by 1.2957. And you want to keep lots of numbers here. Okay, so we're going to see what those numbers. What's that? That would be 1.000. Okay, what about 1.7275 divided by 1.2957? 1.333. Okay, well, you can't have, so this would be iron 1, oxygen 1.333 as a subscript, and that just, we can't have that. So we're going to have to now multiply it by a certain number. And what you do to one, you got to do to the other. Because this is 3, I think I can multiply it by 3 to get a whole number, because I need whole number subscripts. So 1 times 3 is 3, and 1.333 times 3 is 3.9997, which rounds up to 4.0. So now I can say that this is iron 3, and this is oxygen 4, and that is the empirical formula for A. All right, so let's try the next one. We are going to change the percent to gram, 58.53 gram of carbon, and then we're going to convert that to mole. So I'm going to look at the periodic table and see that's 12.011, and so we're going to get the mole of carbon there. 58.53 divided by 12.011, that's 4.873 mole of carbon. Then we're going to do this with hydrogen. 4.09 gram of hydrogen divided by 1.008 gram of hydrogen for 1 mole of hydrogen. So 4.09 divided by 1.008, that is 4.0575 mole of hydrogen. And then we're going to do that with nitrogen. 11.38 gram of nitrogen. And nitrogen is 14.01 gram of nitrogen for 1 mole of nitrogen. So we take 11.38 divided by 14.01, 0.8122769 mole of nitrogen. And then oxygen, 25.99 gram of oxygen. divided by 16.0 gram of oxygen for 1 mole of oxygen. 25.99 divided by 16, 1.624375 mole of oxygen. Okay, so we've done step 1 and step 2, where we converted the percent to gram and then divided by the molecular mass to get moles. And now we would like to see what the subscripts are. So we're looking at C. We don't know what that one is. Hydrogen, we don't know what that one is. Nitrogen, we don't know what that subscript is. And oxygen, we don't know. So what we need to do now is we need to divide all by the lowest number. So we got 1.6, 0.8, 4.0, 4.8. So 0.8122769 is the lowest number, and that's going to be 1, nitrogen. And we have to do that with all of these, the same number. And when we try to get whole numbers for the subscript, 4.873 divided by 0.8122769, 5.999, so that's 6. 4.0575 divided by 0.8122769, that is 4.995, which is 5. Hydrogen. We already have the nitrogen. 1.624375 divided by 0.8122769. That is 1.9997, which is 2. Oxygen. So now we know it is carbon 6, hydrogen 5, nitrogen 1, so we don't put that on there, and then oxygen 2. And that's how you do the empirical formulas. Okay, TNT, trinitrotoluene, that is dynamite. You might know that AC/DC song. Gives you the composition. What is the empirical formula for TNT? Well, let's do the percentage. 37.01 gram of carbon, and then we convert that to mole, gram of carbon for 1 mole of carbon. I'm just going to put all these out here. 2.22 gram of hydrogen, 1.008 gram of hydrogen for 1 mole of hydrogen, 18.50 gram of nitrogen, and 14.01 gram of nitrogen for 1 mole of nitrogen. Of course, I'm finding these values on the periodic table. 42.27 gram of oxygen divided by 16 gram of oxygen for 1 mole of oxygen. And now I'm going to get my calculator. 37.01 divided by 12.01. 3.081598668 mole of carbon. 2.22 divided by 1.008 is 2.202380952 mole of hydrogen. 18.50 divided by 14.01, 1.32048538 mole of nitrogen. And 42.27 divided by 16, 2.641875 mole of oxygen. And now what's the lowest number? 2.6, 1.3, 2.2, 3. Okay, so we agree. 1.32. And I do all these numbers because it might make a difference in that whole number. Because it's nice if I don't have to multiply, because it makes it easier. I'm going to divide each one of these. Now we know this one is 1, so 1 nitrogen. And I'm going to have to multiply because I do know the formula for TNT. All right, well, let's see what we got. 3.081598668 divided by 1.32048368. That is 2.333. 2.2023895 divided by 1.320485368. 1.6678, 2.641875 divided by 1.320485368. That's 2.000. So we got 2, that's a whole number for oxygen, whole number 1 for nitrogen, but these are not whole numbers, and could we multiply them by 3 with the 0.3? 2.333 times 3 is 6.999, which would be 7. So what we do to 1, we got to do to all of them. So that's 7 carbon. If we multiply this by 3, does that work out? 1.6678 times 3? Yes. So that's 5.00, so 5 hydrogen. And then we have to multiply these by 3, so that's 3 nitrogen. And multiply that by 3. 3 times 2 is 6 oxygen. So the empirical formula then would be carbon 7, hydrogen 5, nitrogen 3, and oxygen 6. And that would be the empirical formula. What information is needed to determine molecular formula? So you need the molar mass, the actual molar mass of the compound. So, and then what you would do is you would take so to find the molecular formula, you'd have to take the molecular formula mass and you would divide it by the empirical formula mass, and that's going to give you a number, and that is the number you multiply the subscripts by to get the actual formula mass. What is the percent composition by mass of each element in the following compounds? So how do you do that? Well, you have to take the part over the whole. So let's do the whole sulfur dioxide. So you have 1 sulfur, 32.066. You have 2 oxygen, 2 times 16.00. And the whole then is, and let's do all this out, 2 times 16 is 32, and you'll see why. So 2 times 16 is 32 that belongs to oxygen, plus the 32 that belongs to sulfur, gives you a whole, this is your whole, 64.066 grams per mole. So the percent for sulfur is the part that belongs to sulfur, 32.066 gram per mole, divided by the whole, which is 64.066 grams per mole, times 100%. So now you do 32.066 divided by 64.066 times 100, 50.05% sulfur, and then you would do 32 divided by 64.066 that belongs to oxygen times 100%. So now you do 32 divided by 64.066 times 100, and then that is 49.95% oxygen. And these numbers, since there's just 2 things in there, should sum up to 100%. Okay, let's do copper chloride. So copper on the periodic table has a formula mass of 63.546 gram per mole. and you have 2 Cl, so 2 times 35.4527 grams per mole. And we'll go ahead and figure that out. 2 times 35.4527. That is 70.905 grams per mole that belong to the chloride. And then we add that to the 63.546 to find out the whole, which is 134.45 gram per mole for the whole compound. And now we can do the percent that belongs to copper, would be the part of the copper, 63.546 grams per mole, divided by the whole, 134.45 gram per mole, times 100%. And so 63.546 divided by 134.45 times 100. And that's 47.26%. Now, since there's just the other part is the other thing, we could just subtract that from 100, and then the percent of Cl is 52.74%. And you don't have to, so it's 2 ways you can do it. Okay, let's do C. Okay, so we have 3 sodium. So this is 3 times 23. We have 1 phosphorus, which is 30.9738. And we have 4 oxygens, which is 4 times 16. So we'll do 4 times 16 is 64. We already have phosphorus. 3 times 23 is 69. And then let's add up the whole, which is 69 plus 30.9738 plus 64. The whole is 163.9738 grams per mole. And then, so the percent that belongs to sodium would be the part of the sodium, 69, divided by 163.97. And so 69 divided by the whole times 100 is 42.08% belongs to sodium. The part that belongs to phosphorus then would be 30.9738 divided by 163.97 times 100%. So now we do 30.9738 divided by 163.97 times 100. That gives you 18.89%. And then the percent that's going to belong to oxygen, well, you can sum these two up and subtract from 100. So add the 42.08, that gives you 60.9, and you subtract that from 100, so 39.03% will be oxygen. Then we have magnesium nitrate. This is our last one. All right, so magnesium is 24.3050. Nitrate, we have 2 nitrogens, 2 times 14.01, and we have 2 times 3 is 6 oxygen, 6 times 16. We're going to add these all up. 2 times 14.01 is 28.02 grams per mole. This is grams per mole for magnesium. And then 6 times 16 is 96.00 grams per mole for oxygen. We're going to add up the whole molecular formula. 24.3050 plus 28.02 plus 96, 148.325 gram per mole. And then we're going to do the part of the whole. So percent of magnesium is 24.3050 divided by 148.325 times 100%. So 24.3050 divided by 148, 16.3 9% is magnesium. The percent of nitrogen is 28.02 divided by 148.325 gram per mole times 100%. 28.02 divided by 148.325 times 100. 18.89% belongs to nitrogen. We can add that up with the 16.39 and subtract that from 100, and then we get the percent of oxygen is 64.72%. Calculate the molarity. Okay, so molarity is big M, and that is moles of solute. So whatever is the little guy, the little amount of substance is added to the solution. So here this is a solute. I think the little guy is solute. Solute shoe, the little one, over the liter of solution. Okay, so what we're going to do here to find molarity, you have to convert gram to mole of the solute, and then you're going to divide by the liter of solution. So 122 grams of acetic acid, this is vinegar. And how do we get to moles? We're going to have to add up that molar mass to get to 1 mole of acetic acid. So to get to moles, we have 2 carbons, we have 4 hydrogens, we have 2 oxygens. So 2 times 12.01, 4 times 1.008, and 2 times 16. And so the molar mass would be 60.05 gram per mole. So 60.05 gram per mole. Now we take 122 grams, divide by 60.05, and we get 2.0316 moles. Mole of acetic acid, and then we're going to divide by 1 liter. So then we're going to take this and we're going to divide by 1 liter, and that gives us we'll use 3 significant figures, 2.03 big M. Okay, let's do the next one. 185 grams of sucrose, C12H22O11, and then we do grams of sucrose into mole of sucrose. And so how do we do that? Well, we have 12 carbons, so 12 times 12.01. We have 22 hydrogens, 22 times 1.008, and we have 11 oxygens, so 11 times 16. So let's see what we have here. 12 times 22 hydrogens. Did you get 342.296 grams per mole? So we put that 342.296 grams per mole. And you have 185 divided by 342.296, and that gives you 0.5405 mole of sucrose in 1 liter solution. So now you can divide by 1 liter, and that's going to give you 0.540 mole of solution of sucrose. Okay, so now let's do the next one. 45 grams of potassium hydroxide. So we got to get grams of potassium hydroxide. So if I look at the periodic table, I see 39.0983 for potassium, 16 for oxygen, and 1.008 for hydrogen. I get 56.106 grams per mole. So 45 divided by 56.106 gives me 0.802 mole of KOH. And then it's in 250 milliliters, but I need liters, so I've got to convert that. 250 milliliter, and there's 1,000 milliliters for 1 liter, and so 250 divided by 1,000 is 0.250 liter. Now I can take the 0.802 mole KOH divided by 0.250 liter, and that gives me 3.21 molarity. So that is the answer. How many moles of sodium sulfate are present in 150 milliliter of a 0.124 molar solution? Okay, whenever you see this, make a conversion factor. 0.124 mole equals 1.0 liter of solution. Okay, and then you're going to use that as a conversion factor. So that is a conversion factor. You don't start these with conversion factors. You have to look where you start. Your dimensional analysis is the given, okay? And that's always going to be a number with a unit by itself. So we're going to start with 150 milliliters of sodium sulfate solution, okay? And we start with that, and then we're going to put milliliters of sodium sulfate. Now, we want to get to liters here, and then what's it asking? It's asking for moles. So we can go from liters to moles using this conversion factor, and we're at milliliters. So do you know how to get to milliliters? So 1,000 milliliters equals 1 liter. So we can do 1,000 milliliters equal 1 liter solution, sodium sulfate, but that's not what we want. It wants moles. So we're going to have to copy down liter of sodium sulfate, and here we have liter of solution equals 0.124 mole of sodium sulfate. And so this gets a 1, and now we know what to do because milliliters cancel out, liters cancel out, and we're left with moles, and we want moles. So 150 divided by 1,000 times 0.124, 0.0186 mole of sodium sulfate. That's how many moles of sodium sulfate are present in that solution. How many moles of sodium ions are present? Well, we can start with 0.0186 mole of sodium sulfate, and then we're going to have to copy that down because that's not what we want. So for mole of sodium sulfate, mole of sodium ions, well, this breaks up into 2 sodium plus and 1 SO4 2 minus. So we have, for 1 mole of sodium sulfate, we have 2 moles of sodium ion in solution. So now we can take 0.0186 times 2, and that tells us we have 0.0372 mole of sodium cation, and these cancel out. How many moles of sulfate are present? Well, we have 1 mole of sulfate, so we're going to have 0.0186 mole of sulfate anion. Okay, so our last question, calculate the moles and the mass of solute in each of the following. Okay, so once again, we're going to make a conversion factor. 1.50 mole of KCl equals 1.0 liter of KCl. And this is our given, so we start with 2.50 milliliter, and we're going to say milliliter at the bottom. Now, so here we're going to need to go milliliter to liter, so we need 1,000 milliliters equal 1 liter, and it's asking for moles. So we can go milliliter to liter, and then we can go liter to mole. And then it's just a matter of writing in the numbers. 1,000 milliliter for 1 mole, and for 1 liter we have 1.50 mole. And so now we get our calculator, and we can do 2.50 divided by 1,000 times 1.5. 0.00375 mole of KCl. Okay, but it also says the moles, so we calculate the moles of solute, but it also wants the mass of solute. So how do you go from moles to mass? Yep, you do the molar mass. So for 1 mole of KCl, we have to figure out how many grams of KCl we have. We look at the periodic table, and we see potassium is 39.0983, and the chloride is 35.4527. So that's 74.55. 0.00375 times 74.55. We have 0.2796 grams of KCl. And that's something you could actually measure on the weigh balance. All right, let's do the next one. Same thing. We start with, well, let's make the conversion factor. 2.05 mole of potassium sulfate equals 1 liter of potassium sulfate solution. So you have 250.0 milliliters. You gotta go from milliliter to liter, and you go liter to mole. And so 1,000 milliliters for 1 liter, and then we have our conversion factor here. For 1 liter solution, we have 2.05 mole. So 250 divided by 1,000 times 2.05. 0.5125 mole of sodium sulfate. And then it says for the mass, so then we just convert the mass to the moles. 0.51 are the moles to the mass. For 1 mole of sodium sulfate, how many grams of sodium sulfate do we have? We got to look at the molar mass. So we have 2 sodiums, 2 times 23. We have 1 sulfur, which is 32.066. And we have 4 oxygens, which is 4 times 16. It gives you 142.066 grams times 0.5125. And you have 72.80 grams of sodium sulfate that you must measure out to make that solution. And you would put it in 1 liter. And that wraps up chapter 4.